Says I'm live, but this wheel is still spinning. Ah, there we go. Well, good morning, folks. Thank you. Welcome to the second go around, I guess, on, that's fine, it's right there, on altimeters at the virtual NARCON. So let's see. I don't see. I guess I should look at this and see if we've got. Oh yeah, a bunch of people here. Okay, very good. Well, I'll stop waffling around and get on with it. Sharing the pitch. Well, come on. Oh, come on, for heaven's sake. Oh, I'm still sharing. All right, I'm sharing the window. That's the problem. I'm already sharing a window. I need to stop it and then share the right thing. This is the right thing. And play. All right, here we go. So, as kind of a takeoff from last year's, we're going to talk a little bit more about what else the altimeters can tell you besides just how high did you get. As you've been hearing in other presentations, the chat window is for whatever you want to chatter about amongst yourselves. I'm not going to try and pay attention to it. I will try and pay attention to the Q&A window, and I actually have myself logged into this presentation from my iPad next to my computer here, so I can see the chat window while the pitch is running, or see the Q&A window while the pitch is running. And hopefully I'll get to answer a few questions if I'm not too verbose before we get there. And it doesn't look like I'm off to a very good start on that point, am I? Okay, here we go. Just for those of you who don't have any idea who this guy is, I've got a short introduction, and then I'll talk a little bit about some things that have happened after or since last year's presentation, especially with respect to competition use, and just a very fast blast through the basic principle of how barometric altimeters work, and then we'll get into the meat of today's presentation, which is to look at other stuff that you can learn besides the apogee, and some strange things that happen in the data, and whether or not you should care. And as I say, if we have time, we'll do some questions at the end. So I was a model rocketeer when I was in junior high and high school back in the late 60s and early 70s. I went to the New Mexico State Science Fair as a 7th grade based project. After getting a mechanical engineering degree, I came to work for Boeing up here in the Seattle area, spending most of my time in the commercial, and retired after just about 38 years. My main passion during most of that time was RC, electric powered airplanes. And I always enjoyed testing things. So I just had a motor test stand, and I had a bunch of meters for that sort of thing, and wrote articles about equipment. Came back to the hop to rocketry a little over a dozen years ago. And of course, since I like to gather data, gathering or altimeters immediately came to my attention. And so I've amassed quite a collection of these things, and I've used them a little bit in competition. And I've also done some testing for several makers. I did a project for NARM 61 for R&D. I'm currently on the slightly revised version of the altimeter usage article that's in the current NAR member guidebook, and I talked about altimeters in NRC competition last year, and they didn't fire me, so I guess here we go. I got invited back. All right. So last year, at the very end of the presentation, I put up a picture similar to this, but not the same, letting people know that the two devices on the right, and especially that tiny one down in the lower right-hand corner, were in the process of being approved for competition use. Well, that has subsequently happened, And as I understand it, there were quite a few of these flight sketch comps, which is what that one is in the lower right-hand corner of the picture, in use at NARAM this past summer. By all reports, to good effect. So as I say, they were both approved for competition use late last spring. And well, I'm getting ahead of my own bullets. I do that a lot. And also there's another new altimeter out there, which is based on the Polish Adral Alt BMP that North Coast Rocketry sells, that has the ability to fire a single pyrotechnics channel. I think that's an attempt especially for altitudes flying where we can never get a long enough delay to provide an alternate approach. I have not messed with this one. I've seen one. So I can't really address how well it works or not, but it's out there if you can get one. Unfortunately, of course, all of these things are hard to get right now because some bit or other is on a boat or just back ordered from manufacturing. I might as well get this out of the way right away. Flight Sketch is anticipating having the necessary parts to build another batch of minis, which is the one in the upper right-hand corner of this image, sometime later in the spring, somewhere between February and April, depending on which supplier comes home with which of the part that he needs. He has no idea when the comp will be available again. It may or may not be any more of them before next NARAM. Okay, and one other interesting thing is that there's a rules change proposal out there right now to do away with optical tracking in NAR competition. And this was submitted by the gentleman who writes the contest manager software and is often the fellow doing the data work at NARAM. I'll just let you read the bullets on there. The main thing I want to say here is any NAR member can vote on competition rules, and you just have to find your way to the right spot on the NAR website, and the link is at the bottom, or the URL's at the bottom of this chart. For you to go there. Basically, optical tracking is so much more complicated, as everyone who's ever been involved with it knows, than flying altimeters, that's felt that it's about time we just went with all altimeters. But there's a lot of discussion about what to do with the existing records that have been set with optical tracking. Okay, very quickly, electronic altimeters use a pressure sensor, a very sensitive pressure sensor, that in conjunction with a well understood model of the atmosphere, which is pretty good, allows you to take a pressure and a temperature and calculate an altitude. And so your basic altimeter algorithm will somehow set the current pressure when you put the thing on the pad or just before launch, looks for a pressure drop to decide it's flying, watches and keeps track of the pressures as they decrease as the rocket goes higher, and it either calculates on the fly or in an app after the fact what the altitudes were, and from that figures out, with some filtering, which is really the hard part, what your actual apogee was. Actually, we'll see some examples of where that's difficult for the altimeter, and as we get into the body of the pitch here. Anyway, and if you've got an altimeter that can store multiple data points, and you've got a computer to get the data back out again, whether that computer is a desktop or it's your phone, then you can see and calculate all kinds of interesting data. And that's really what I'm here to talk about today, now that we're 10 minutes in. So this is my third NARCON presentation about altimeters. Dave Davis, who was organized the Seattle NARCON in 2015, invited me strongly to give my first one, which was way too heavy on how important static ports were, as it turns out, and as I've learned since then. But near the end of it, I had, or up in the front when I was talking about why do we have altimeters, I had this chart that says, and we have other questions. How fast did it go? Did the deployment happen when it should have? How many G's did it pull? Which of course requires an accelerometer, which a lot of altimeters have these days. How long did the motor actually burn? And so that you can compare that with what it was supposed to have done, and also the delay, in fact, and on and on. So more and more questions. Well, by looking at the data from a recording altimeter, you can answer all these questions or infer the answers to all these questions, and a few more things to boot. And so here we go. So if everything goes smoothly, um, and you download the data from an altimeter and plot it out either with their app or through some of the graphing program. This is flight sketch data. Most of what you'll see in this presentation are data downloaded from a flight sketch device, either a mini or a comp. And often the graphs are on this that I'm showing are screenshots from the online log. Excuse me. Which is why on almost all of them I managed to put where these data are, so you can go grab the file and download your own, or you can see and manipulate this graph on the website. Anyway, this was my Estes Leviathan flown over at Sod Blaster 3 in Tri-Cities just this past September. And this flight went very nicely. You can see this nice smooth boost, and hardly any rippling there at the top, indicating that the deployment was about the right time. You can see that it was descended with a chute release on it set for 500 feet, so it fell at a certain rate with the chute bundled up, and then when the release released, it took about 100 feet for it to get fully open and a nice smooth touchdown. So this is what a nice smooth flight looks like. And from this, you can pull some data just from the graph. As I say, you look a little closer at the top and you can see the little ripple there where things started to get bounced around. And that's a pretty good indication that a deployment event happened, or the rocket came apart in some fashion, deployment being the one you want. And then you can just from the graph, you can calculate descent rates, and you can see it fell at about 40 feet per second until the chute opened, and then it dropped to just over 20. And you can also see that the chute took about 130 feet, assuming the released it right at 500 to get fully open. And if there's an accelerometer in the altimeter, as there is in the flight sketch devices, and also in Jolly Logic Altimeter 3, then you can see what the motor was doing from acceleration data. So here's since it's so long and skinny, I broke it into two pieces so that this spike on the right in the upper graph and the smaller spike on the left of the lower graph, that's the same point. That's the deployment event. But you can see a curve that looks an awful lot like the time thrust curve of the engine. You can see that it was kind of bouncing around as you'd expect with the chute bundled up as it was falling. And then things got nice and quiet once the chute opened, and then there was a bounce when it hit the ground, which I think is all on the next chart. Anyway, there, yeah. And here you can also see just from the distance between when the thrust fell off and the big spike at ejection that the actual delay on my drilled to 8-second delay CTI motor was 9.5 seconds. But I think I knew it was, I think I wanted to bias it a little long because I knew that 8 seconds was a little short for that particular combination. At least that's my making it look right after the fact explanation. But anyway, you can see clearly 9.5 seconds delay, and that the curve from the actual accelerometer, this is just the same spot just stretched out, so you're only seeing the first 1.5 seconds or so, matches the certified time thrust curve pretty closely. You see the motor was certified to have essentially this even thrust across its whole burn, and of course the rocket the acceleration would decrease during that time as the speed went up and the drag went up. So this all looks pretty consistent to me. And the certified burn time is in 1.35 seconds, and by golly, that's just about where that fell off at. And as I mentioned before, here you can see it kind of bouncing around as it's falling, and then smooths way out when the chute opens. Then another good kick that was as good as the deployment event when it first hit the ground. Um, a lot of the altimeter makers also calculate velocity, often from the barometric data or a combination of barometric and accelerometer data. Flight Sketch does the combination. And you can see that the Leviathan hit 400 miles an hour at burnout. And you can see the velocity change as well when the chute opened. And just for grins, here's what a two-stage model looks like. This is just a little bitty Estes Checkmate, which had a comp in the payload section, but you can see the spike of the A10-0, and then a different shape curve with the A34T that was in the second stage, and that the actual 4-second delay, quote, quote, was 2.6 seconds long. And also, and I've watched this model fly a bunch of times. I've probably got 50 or 60 flights on a couple of them. You'll see that there's a flat spot in the velocity curve up here, and that the acceleration during the long tail on the A10-0's thrust is right at 0 Gs, or 0 feet per second squared, because the thrust just barely has enough to keep it going. It doesn't accelerate at all. It just keeps on going at the speed it was at the end of the boost spike, which I found really interesting, that the data matches what I keep seeing when I fly this particular model on those motors. Okay, so those are examples of essentially things working the way they should. What if it doesn't quite? So one of the obvious ones is if your delay runs long. And so here's what one example of what that looks like. This is one of my Nova payloaders on a QJet White Lightning C-18 that was marked 6 seconds for delay. And you can see the velocity curve turns around at 8.92 seconds. So you can pull this off of this graph, and that it was moving at 113 feet per second in the downward direction when that happened, or 77 miles an hour when the actual deployment event happened. Here you can see it pretty darn sharply as the change in the shape of the curve. Well, looking at the accelerometer data, that was really an 8.3 second delay. Kind of explains why it looked like it ran long. Here's another example that's not quite so dramatic. This was last June. This is a Lock Iris so-called park flyer. This is their 1.6 inch diameter model that has a 29 millimeter motor mount in it. But they claim can fly on something as low as a C. This had an F39 White Lightning with the curiously marked delay of 9(6). Apparently the certified delay time for these things is 6 seconds with the NAR, but for some reason Aerotech also calls it 9 seconds. And I've seen, as you'll see as we get a little further into this, all examples all over the map in that range. But again, you can see that it starts a ballistic descent here before the ejection event, which perturbs the curve. Yeah, brought in my inset. You can see it much more clearly here, that it's pitched over, and then the ripple from the ejection, still not particularly violent. And then it was from the velocity curve, 38 feet per second at deployment, not too bad. So the delay on this particular flight was actually 8.8 seconds, again from the accelerometer data. And yet the first time I flew this model on another motor, I think from the same package, the delay was 6.2. This is an Altimeter 3 plot of the first flight of the same model from back in last April up at 60 acres. So let's look at the other end of the case, or other case, and this is where the competition folks are most concerned about, because this, especially for altitude, happens all the time. What if the delay is too short? Well, you can see a kind of a little backward spike before the peak that shows that the ejection happened before the rocket had stopped going up. In this particular case, this is just a little BT-50 base model called a Cadet. So you'll see more about this guy a little bit later. Here's the acceleration curve from that same flight. And note that the C63 gave us 3.1 seconds. Not bad. I was out there actually testing the short delay case for Russ and Dan Wolf on the contest board. So I was intentionally putting something in it that I knew was going to be too short, because we were looking for overshoot at the beginning, or overshoot in the curve here that we were seeing in earlier versions of the flight sketch software. Just for your amusement's sake, here's I had a micro peak in the payload section with the flight sketch, and this is the graph from that. And you can also even see in this one that the deployment was a little bit early, because of the little spike there before at the very top of the curve, but early in the shape of it, early in the parabola, if you will. Here's another too short delay example. It looks a little bit different. The short delay ones have a wider variety of what the curves look like. Again, delay shorter than Mark. This was a C12-4 fast-jack Q-jet, and really unusual for an Aerotech motor. Its delay was actually 3.1 seconds. And so hence the basically chopping off the ascent and making it just stop rising and just kind of hang there for a bit. So a lot of people, especially since the flight sketch has been released, have been flying them in with the parachute or the streamer or whatever, and not in a dedicated compartment. And I know that multiple different makers will say, well, you can do this if you really want to, but please protect the altimeter from all the stuff that it's going to get exposed to if it's not in a nice little payload section of its own. And I reiterate, or I certainly agree from my own experience, that you need to do that sort of thing. So I use these little fleece pouches on the flight sketches, and Dino Shoots makes them out of vinyl, and they even make a pouch for the Altimeter 3, or which is actually, is in a plastic case already, and is sold with the idea that you don't need to protect it, don't necessarily need to protect it if you're going to fly it in the main body of the rocket. But anyway, there's ways to do it, and you should definitely protect them, or you get all kinds of nutsy things. We'll see that in a minute. But one of the things you have to be aware of is that static ports and whatever else, other ways that air can get in and out of where the altimeter is flying can affect what it sees. And we're going to see some examples of that here in just a few. For instance, if the air is leaking around the motor at the base of the rocket, air can leak in there and make the pressure drop and make the altitude look like it's going artificially high during boost. So these are two curves from the same flight, one of which was from a flight sketch mini up in the little dedicated payload section, and the other one, the one I just brought onto the screen, was down, or was underneath, up just on top of the parachute in the main body of the rocket. And you can see, as I add this in, that there's a little spot there during the boost phase, and it happens to coincide very nicely with burnout, where the altitude seems to take a sudden drop and then rise back up again. And what's going on here is that the air is leaking out of the body of the rocket around the motor, and it's going because of base drag and the exhaust plume. There's a low pressure area at the bottom of the rocket, and so the air is leaking out, and it's causing the pressure sensor that's on the altimeter inside the body of the rocket to think it's rising faster than it truly is. And so when you plot the data, you get this little kink. And depending on how fast you go, the kink gets more dramatic. This was an Estes C6. So take the very same situation, same model, same altimeters, but put a QJet C12 in it. Oh, I'm getting ahead of myself. First of all, this is the, sorry, I got ahead of myself. This is the same data from those two flight sketches on that flight overlaid in a tool called Magic Plot. So you can see both curves. Once the motor's burned out and the pressure sort of settles in the body, they follow along pretty closely. It's interesting that the one that was in the body sees the short delay thing a little more dramatically. But you can also see that that spike in the altitude graph lines up perfectly with the point of the velocity graph, and also where in the acceleration graph where the motor burnout happens. Anyway, so a more dramatic example is with the C12. But before I show you that, I'll show you what this actually looks like. So I just took the top 2 inches of this model and put a coupler and a ply disc in it and made a separate payload compartment. You can see a pinhole right there. That's one of the static ports. There's 3 of them that size in this little 2-inch long BT50 compartment. And then there's static ports here at the about 1 inch down from the joint. And so one of the flight sketches gets stuffed in with the parachute, and the other one gets, or in the streamer in this particular case, and the other one gets put in the payload section. So C12, here's much more dramatic example. Again, the boost or the curve from the one that was up in the payload compartment looks nice and smooth, just like you'd expect. And the one that was in the body, my goodness, look at this spike, and then drop off and then climb out again. Because it not only is accelerating faster, but because it's going faster at burnout, it slows down much more quickly from drag. So you get this lovely spike. And here are the data from those two altimeters overlaid. And again, but it's you can see it all lines up nicely, but it's really busy over there. So here's a zoom in on just the first couple of seconds of the flight, because the motor burn time on a C12 is about a second. And there again, you can see very clearly that the end of the thrust curve and the peak in the velocity, or in the peak in the velocity graph, and the peak of that point in the altitude graph from the one that was in the body all line up perfectly. And the blue line is the altitude, time versus altitude, for the altimeter that was in the payload section. So up to now, this has all been data of my own, from my own flights. But as I was thinking about this talk, I thought I'd go look at some of the other data that other people have posted on the Flight Sketch website, and see if I could understand what was happening to them from their data. And then I contacted a couple of folks and got permission to post their data and talk about it. And they told me a little bit more about the configuration of their models, so that I could, correlate what I saw with and what I get with my own models with what they experienced. So this is a gentleman who goes by the Handle Traction Engines on TRF, and he flew an Estes Goblin from the recent version of the kit, the plastic nose cone re-release, with an FS Mini in a Dynashoots pouch in the body, and flew it on a QJet C12-8, which when I heard C12-8, I thought, oh my gosh, that's definitely going to be too long a delay. And you can, just looking at the altitude graph here, it's obvious the delay was way too long. Its ballistic return till clear down to here, till about 200 feet above the ground. So he also has the peak in the altitude graph from having air leakage around the base or at the base of the model from that gets to where the altimeter is. And the actual delay on that particular C12-8 was 9.4 seconds. So yeah, way too long. And so he finally got the streamers deployed when the thing was coming towards the ground at 112 miles an hour. Here's one that's even more curious looking. This is a gentleman named Keith Storer, who was working with a bunch of students, and they were flying the Estes green eggs, doing some kind of a target altitude competition. And but they were putting the flight sketch up in the tip of the plastic nose cone, and there were no static ports in the payload tube, but the air could get into the payload tube from that hole that's in the bottom of the adapter there. And this one was got all kinds of interesting stuff going on. So first of all, he too has the base and model leakage spike because the motor tube on a freshly built green eggs doesn't grab a C11 that tightly. So there's air leakage at the base of the model. And then this was a glaring example of what happens when the ejection charge goes off and the model doesn't instantly open up. You get this huge downward spike in the calculated altitude because, of course, you're pressurizing the inside of the tube, raising the pressure, so lowering the altitude calculated. I've seen this in lots of different flights over the years, but this one was a really dramatic example. So I thought I'd grab it. And as you can see, the altimeter must have been bouncing around or come loose inside the payload section as it was coming down, because there's just all kinds of noise in both the accelerometer data and the barometric data. And looking at that, I have to assume that either the chute stripped or didn't open properly. And I don't think I got confirmed from him what exactly happened here as far as the descent is concerned. But just this is what it probably, I dare say, should have looked like. This is my own green eggs that was just flown a couple of weeks ago at the club launch, my club launch, and I've got a piece of clear tape. You can't really see it probably in the picture, but the hole in the base of the payload adapter is taped over so that air can't leak there. And there are 1/16 of an inch diameter static ports drilled in the payload tube. There's actually two sets, one down near the bottom and one up at the top. I discovered when I actually put an egg in this thing that it fits so snugly that I was concerned that it was blocking the static ports at the bottom. So I put another another set at the top. In this particular flight, the flight sketch mini was stuffed up in the tip of the nose cone and then just held up there with a paper towel. But this is much smoother, and this is a same model on the same motor. Okay, one more set of examples. Just last week, my wife and I were at Ocean Shores, Washington, and I usually take something to fly, even when we go over there. And I had an Alpha 3 with me, which I flew off the beach. And the flights this past week were a couple of things showed up in the graphs that I thought were quite interesting. So on this chart, you see on the left, that's a flight from a year ago. And the one on the right is a flight from, well, since January 18th. These were both flights were on SSB-64s from the same date code. But on the one on the right, you can see that same altitude spike that I've been talking about because of motor air leakage, and also obvious, very clear indication of a delay that was too short. This is an Alpha 3 with a streamer, where the flight from a year ago looks pretty darn normal for a streamer model. So what happened? Well, the first thing was I inadvertently conducted an experiment on how big a static ports, or the size of static ports relative to this leakage at the base of the rocket and the influence on it. When I built the model, I just left the roll pattern stickers off. But before we went on this particular trip, I put the upper one on, and it covered over the static ports, which were 3/32 of an inch. diameter, that 3 of them that I had in the upper part of the body tube. So before we went out to the beach to fly it, I said, "Oh my goodness, they're all covered up. I need a pin to poke it out." Didn't have a pin, so I just used the end of an igniter lead to poke little holes in the clear plastic. So I had little tiny static ports instead of much larger ones. So suddenly I had an experiment to compare the effects of the two. And since that got me thinking, I had to go back out after I opened the holes back up to see if the spike in the boost data went away. And sure enough, it did. So on the top left, that's the same graph as from the prior charts of this model. Uh, then the one at the bottom on the left, that's the same chart as from the prior chart as well, the one that big spike. And then the one on the lower right um, is the last flight that I did over there a couple of days later with the holes, the static ports open back up. Um, and that's a liftoff shot that my wife took with her iPhone. Gorgeous liftoff shot on that last flight. So let's look a little closer. Here's the first two, the flight 17 a year ago and flight 19 on the 18th, overlaid with one another. You can see the first one's got a fairly smooth shape, and then the second one's got the early delay spike as well as the spike over here for the base leakage. And then I put the 3/32 ports back in, open them back up, and the green line is that you can probably barely see because it's sitting on top of the blue one for almost the entire flight. No more spike. But as I mentioned, the delays were shorter, or they both showed, or the flights this past little bit at Ocean Shore this past week, 2 weeks ago, at Ocean Shores were showed evidence of a short delay, and I found out that there's huge variation here. As I say, these motors all came from the same bulk box, and the last year's flight had a 4.4 second delay, a little bit long. Estes delays tend to run a little short anyway most of the time, and that one was actually 4.4 seconds, so it was a little long. But that last flight last week was only 2.8. So I got to poking around a little bit and was reading in the NAR certified motor list, and there's a tolerance on delays that's plus or minus 20% or plus or minus 1.5 seconds. And so with a 4-second delay, or whichever is larger. And so with a 4-second delay, it can be anywhere between 2.5 and 5.5 seconds and still be within what the certification required. So both of these motors were. Here's the acceleration curves laid over the top of one another. And the main thing I wanted to show here was the difference in the delays, and it's much more clear. Here's the first 7 seconds, and you can see that green is the flight from on the 21st of the month this year, and the blue is the one from the 22nd a year ago. And you can see the huge difference in the delay from the huge difference in where the spike at deployment happens. And yet the the thrust curves overlay pretty well. So should you care about this stuff? Well, it depends on what you want to know. If all you want to know is how high it went, then all this other extraneous stuff, as you can see from these graphs, usually you get an apogee value that's plausible, pretty good, usable in contests even anyway, because the spikes for base leakage and such happen. They don't go so high generally as to make the altimeter lie about how high it really went. Although I certainly would recommend looking at the graph if you're submitting a flight sketch or altimeter 3 to the returns desk at a contest, just to be sure. Well, you're going to see the graph anyway when you download it. You can't really see the data or download the data and not get it. Anyway, also you can get, even with the air leakage funnies, the accelerometer is going to tell you about delays and so forth pretty accurately anyway. It's just going to be noisy data. So if you really want to see what's really going on for the whole flight, it's really better to have the altimeter riding someplace where it's not getting all these extraneous influences from air leaking in and into or out of the rocket from other places and other sources or other pressure sources like ejection charges, which I just said. So there, I don't need to read that. Yeah, isolated is better if you like nice clean data. And just because I've been showing essentially all flight sketch data except for that one chart that had an altimeter 3, here's that Loch Iris Park Flyer again. This was flown just a couple 3 weeks ago up at 60 acres. And this is what the data from the altimeter 3 looked like. And this one, the delay was just about perfect. And there was also a flight sketch on board that same flight. And so here's some comparative data. I just had the flight sketch in the pouch. I just taped it to the altimeter 3. So they were both hanging from their lanyard in from the nose cone in the payload section. This Loch Iris is a lovely big payload section without me having to modify it. And you can see that the accelerometer data matches pretty well. So, 0.02 of a second difference in what they calculated the burn time to be. The timed apogee that flight sketch gave me was 8.34 seconds, and if you add the burn time and the delay time from the altimeter 3, you get 8.30, so that's pretty darn close too. And the altimeter 3 said the ejection delay was 7.1 seconds. So that's in this range between the 9 and the 6 on these Blue Thunder F-39s. And this is what the plotted flight sketch data looked like from that same flight, just to show that, yeah. Okay, so which devices can you use to do this stuff with? Oh, and it looks like we're actually going to have a little time for questions because I'm almost done with my charts. If you want barometric, if you want to just time versus altitude curves, lots of choices. The Perfect Light Peanut and the Stratologger, Altus Metrum's MicroPeak, and the Adral Alt BMP, which is now sold by North Coast as the Max Alt, can all give you time versus altitude plots. And you can also download the data to some other analysis program from all of these, although getting it out of the Adral and into a form that you can actually use is a little difficult because what it exports is just times or just altitudes. And you have to know what the sample rate is from what you told it when you set it up. And then you have to kind of back calculate stuff to lay that in. I think, I have not yet tried, but I suspect that Chris Irving's Egg Timer Ion will also work great for this kind of stuff. If you want to add in an accelerometer, the main choices are the flight sketch devices and the altimeter 3. And yes, I know you can't buy either one of them right now. Altimeter 2 also has a accelerometer in it, and it can tell you a lot of the times and so forth for different events. It just can't give you the graph. So a lot of the things you're looking for, if you're looking to find out, well, is my delay too long or too short? Was the motor burn what I was expecting it to be? And all that fun data about accelerations and speeds. You can get that from Altimeter 2. You just have to cycle through the screens and write it down someplace. And it calculates, well, yeah, the bullets there, you guys can read. So if you were wanting to suddenly go fly and get a bunch more data and you didn't already have one of these other devices, I think you can actually buy Altimeter 2s right now, although I'm not positive of that. Yay, electronics parts shortages all over the place. And I think some of the Perfect Light, the Peanut may well be available too, because that's one of the TARC altimeters. And I see a question about various plotting apps over here. So here's, those of you who've seen the my article in the NAR member guidebook have seen a version of this figure before. These are all graphs plotted by the applications that you need to use these various altimeters. All these altimeters rode on the same flight. So you can see that they all present the time versus altitude data in a similar fashion. It's not the same, but it's similar. That's just to sort of give you a sense that they all do that in some way or another, even though I focused on flight sketch data for this presentation so far. So this is the windup. I find it fascinating to learn all these things about what's going on with the flight and when it happens. And hopefully some of you will enjoy learning this sort of thing too. And now you have a little bit better idea what the graphs are trying to tell you if you didn't before. So we'll flip over to the questions. I guess I'll stop sharing this so you get stuck looking at me. So starting at the bottom of the questions, can you comment on the difference between velocity calculations derived from barometric data and velocity derived from accelerometer data? I could probably try, but I'm not sure I could say anything intelligible because I'm not entirely sure how the accelerometer based velocity data are generated. I mean, it requires an integration of the accelerometer data. That much I can say, and that software has to be has to be able to do the integral. And I know that Russ Parrish in the flight sketch devices, and he may well be on and can correct me if I say this wrong, basically uses accelerometer data for the boost phase and then cuts over to the barometric on the descent phase. But he gets his maximum velocity and that kind of thing from the altimeter data or from the accelerometer data. And I'm pretty sure that that's also the case with Jolly Logic. Okay, so I started to touch on this a little bit. What are the plotting apps I'm using? Each altimeter does in fact come with its own. The overlaid graphs where I put more than one flight's worth of information on top of one another, that those were done in an application called Magic Plot, which is available for both, or for Windows and Mac OS, and I think even Linux. And I've ultimately wound up buying their academic version rather than using the free version because it let me have multiple axes on. But you can do the basic comparisons with just the free version. But all the other graphs were off of the apps, or in the case of the flight sketch data, a lot of it there's also an app in their website. You can go to anybody's flights and pull them up and see the plots that are done in your browser. And that's where those pictures came from. How do you calculate required diameter and quantity of static ports? I wrote an article for the Apogee Peak of Flight newsletter here some months ago that went into that to some degree. I do it by guess and by golly, pretty much. Every altimeter maker has some guidance, and it's all over the place. There are 2 or 3 good calculators out there, and I really suggest that you just go to the Apogee website and find that issue of the newsletter. I should know what number it was off the top of my head, but I don't. It's about 6 months old, where I cited a couple of ones that I found to be quite usable. But I generally overdo it just because in small models it's hard not to, and I've found that overdoing it a little bit is not a big deal generally. Leslie Bradshaw asks what about the Raven? I have no experience with deployment devices, at all. So I have not dabbled in devices of the class of the Raven. Um, and you're going to tell me now that, of course, the Raven is not a deployment device, and if that's the case, then I'm just all wet here. But I have no experience with it, so I can't really address it. So that's a terrible answer, but that's all I got. And Donald, well, he's a prolific questioner. Asked, do I have a favorite? Well, as you can tell, I've been flying Flight Sketch a lot. It kind of depends on what I want to do. But these days, yeah, the Flight Sketch devices are kind of my favorite, even though the app is a little less polished, if you will, than the Jolly Logic, the Altimeter 3 app. Either way, being able to get the data in and being able to control the altimeter with my phone, and then getting the data out and dumped into my phone, and for Flight Sketch also up to the web, without even having to touch the device, is just magical compared to the good old days when you had to pull it out and count flashes or beeps, and then go plug it into your computer at the field, especially for like a micro peak, which only holds one flight, only holds 47 seconds worth of data, so you only get one flight at a time out of it. So you'd have to download the data at the field, or you only fly a particular altimeter once. It works. It actually works very nicely, but it's so much easier when you can do it with your smartphone. So I'd say at the moment, I would say Flight Sketch devices. Raven is a deployment device, but also records barometric accelerometer data. So Leslie, yeah, so you certainly can get all this data that I've been talking about out of a Raven then, certainly. And if you've got one, by all means, go fly it and glean stuff. Brian Baird says, does anyone have a full IMU and barometric package for model rockets? This is getting into Joe Barnard's territory. I would go poke around BPS space, and I wouldn't be surprised if there's somebody else that either has or is working on it, but I'm not aware of anything besides the thrust vector controllers that Joe Barnard is doing, having a full inertial measurement units in them. Let's see, Doug, do you have any insights from altimeter data and high performance parachute duration models, say dancing thermals or in RC gliders? I flew altimeter loggers in airplanes quite a bit when towards the end, back when I was actively doing that. That's kind of how I got into altimeters here. But as far as optimizing performance for competition, I was never really an RC glider guy. There are altimeters that have modes. The Altimeter 3 has a mode, an airplane mode, so it won't just conclude that it's done flying when it's come back down to the ground. So you can see, flight like the now no longer available Eagle Tree or Medusa loggers could tell you, or the Eagle Tree in particular was able to give you a whole flight's worth of altitude data, either barometric data or GPS data, in fact. But as far as optimizing for performance, I've never done anything like that. And I hate chasing PD models, so I've never even competed hardly in parachute duration, so I'm afraid I can't help you much there. Sorry. Steve Navard from Launch Lab says, how much did Russ pay you for this hour-long infomercial? Well, he didn't pay me anything. I have gotten a few free altimeters because I've done beta testing for him for over 2 years, but that's the extent of it. Let's see, and I've got, since I have the chat up over here now, Tom Dish remarks, black powder and electronics do not play well together. Yeah, it's exactly. Larry Crucio says, does positive ejection spike affect apogee only altimeter readings, or is it filtered out? In general, they try and filter these things out. And I have an Adderall example where the spike was in the data until I turned on the filter on the Adderall app. Not filter can engineer Can one engineer ejection overpressure to get a negative spike? I don't have the slightest idea. Zeke says I'm working on one of those. Let's see, scrolling up through the chat. Okay. Test question, test answer from Todd. Good morning, Ron. Good morning, Jim. Good morning, Ed. Seriously? No more questions? I like it. We've got 4 minutes to spare before we go off to the next presentation. Let's take a quick look at the attendees, just see who was crazy enough to listen to me blather for almost an hour. Wow, that's quite the list. Did Russ? Yeah, Russ was here. Okay, Russ, you'll have to tell that gentleman whose name I've already forgotten all the answer questions. Tell Steve Navard how much you've paid me. Mr. Fitzpatrick. Okay, well, I guess let me go back to the Q&A. Open. No, 0 open questions. So I guess we'll call it good. It's 8:57 Pacific time. I guess you're free to navigate to the next presentation. I'm going to tap the stop broadcast button here in just a few moments. Thanks for listening to me blather, everyone. And that's my wife's grandmother's clock chiming just a little bit early.